Hey everyone, welcome to our next video. Today we are doing 2.7, if my notes would show up. There we go. So 2.7, I know on the last video I accidentally said 1.6. I meant 2.6, but 2.7, and this is analyzing graphs of functions and we're going to do some piecewise functions. And I'll explain what that means when I get there. Now, what's interesting, I always sometimes don't like these titles because it says, graphs of functions. However, we do some stuff in here that are not necessarily functions, but they are relations. But the first thing we're going to talk about is symmetry. And so I've actually brought this up a little bit in the last video. I mentioned that quadratics or parabolas are symmetrical, like around each side. You'll also see that we can see some symmetry in the absolute value functions. Like you see how you can just split them down in the middle and they're the same on each side. That's kind of what we're talking about. But there's different types of symmetry that we can see. So I'm going to show you the different types. So one type is that we can be symmetrical with respect to the x-axis. So a good example of this one would be y squared equals x. And so this is symmetrical with respect to the x-axis. Meaning if you split it down where the x-axis travels, on either side of the x-axis, you have some symmetric, like it's symmetrical. I feel like that was a little weird to explain. The properties here that we're going to see is that negative f of x is the same as positive f of x. So when we go to check for this type of symmetry, we're going to make our y value negative and see what happens. And I'll do some examples, of course, but that's the idea. So if we want to check this type of symmetry to see if we have it, that's what we'll do, is we'll make the y value negative. Then we have symmetry about the y-axis, and that's the type that we see for like regular parabolas, like y equals x squared. So this is symmetrical with respect to the y-axis. So you see, like if we split it right down the middle on the y-axis, it looks the same on each side. For this one, the property that we'll see is if we plug in a negative x, it'll be as if we plugged in a positive x. So we'll get that negative x plugged in is the same as a positive x plugged in. And so to check for this, we will make our x negative and see what happens. And then the last type that we will see is symmetrical with respect to the origin. And an example of this one is y equals x cubed. So this is symmetrical with respect to the origin. So just a reminder, the origin is that middle point right here. And so what we'll see for this one is that f of negative x is equal to negative f of x. To test for this one, we'll actually make both the x and y negative. Is one way to do it, or you can make your x negative and we'll see what happens. So for this one, I like to just make the x negative. But we should see different properties. So like for the y-axis one and the origin one, they're very similar in what we would choose to do. But you'll notice for this one, see how the negative doesn't matter? Like you'll get the same result whether you plug in a positive or negative x. This one we're going to see that actually the negative does matter, and it's going to basically pull out to the front. So there's kind of two ways to test that one, but I kind of like this better. I also want to make a point to tell you that when we are symmetrical about the y-axis, we call this an even function. When we are symmetrical about the origin, we call this an odd function. So first, let's do an example of finding some symmetry. So example 1, we're going to determine if the following are symmetrical with respect to the x-axis, the y-axis, and the origin. So we're going to see if they're symmetrical to any of these. And so for our first one, we're going to do y equals absolute value of x. To see if something is symmetrical about the x-axis, I'll do that one in pink. So what we're going to do to test that is we're going to make our y value negative. So I would do negative y equals absolute value of x. And what I'm hoping to see is that if I simplify this, it would be the same as my original. Or I would see basically this property happen. So same as my original. Well, if I multiply that negative over, I'm just going to get negative absolute value of x. This is not the same as y equals absolute value of x. So no, it is not symmetrical about the x-axis. All right, let's test if it's symmetrical about the y-axis, and I'll do this one in green. For symmetrical about the y-axis, we'll use this property. So I want to check to see if I plug in x as negative, will it be the same result as if I didn't have a negative x? And for this one, well, if you plug in absolute value of negative x, absolute value just gets rid of any kind of negative, right? Like a negative x would be the same as positive x in an absolute value. You know, negative 1 in an absolute value is 1, 1 in absolute value is 1. So this one, yes, they are the same. So we see that this is symmetrical about the y-axis, so we would call this an even function. And then if we want to test for the origin, we can. It's not going to be able to have multiple times of symmetry, but we can check it just to be sure. And so we should see this property up here. So if I plug in a negative x, I should be able to pull that negative out to the front. Oh, sorry, I wrote it wrong. There we go. Well, the only thing that would happen is I would get absolute value of x. So the negative just disappeared. So does not satisfy our property here. So no, doesn't have symmetry of the origin. Let's try another function. So that one was only symmetrical about the y-axis, so it was an even function. Let's do x equals y squared minus 4. And we'll do some tests. So to see if it's symmetrical about the x-axis, excuse me, I'm going to go ahead and make my y value negative. So that means, so what I'm trying to see here is I'm trying to see this happen, right? I think my negative y should be the same as if I plugged in a positive y. So I would get x equals negative y squared minus 4. Negative y squared is the same as just y squared. So I am indeed satisfying this property. So this is symmetrical about the x-axis. Now just to show you the other ones about what would happen, for the y-axis, we're trying to satisfy this property. But what we'll see is if we plug in a negative x, I'm not able to get back to my original. Most I could do is maybe divide everything by negative, but it doesn't do anything. I can't get back to the original. So it doesn't satisfy. And then lastly, if I want to try for the origin, I should expect to see this property happen. So if I plug in a negative x, I should be able to pull a negative out to the front and it be the same thing. So I have negative x equals y squared minus 4. Be careful here because you have the you have like the y squared in your function. So you would want to get your y by itself to really see this property happen. So you do have to be a little careful here. Or you could take it like this. Here's another way to do it. You could say, let's add that 4 over. And the original one, if we had moved that 4 over, we would have had x minus x plus 4 equals y squared. So since these are not the same, or it's not like the negative version of it, let me explain this better. Hold on. Let me restart this explanation. What I'm doing right now is I'm trying to get the y by itself since this is an f of x function. Now I don't necessarily want to take the square root because sometimes that can mess with the signs, but I'm just trying to get the y mostly alone. So if I take my original and I get the y mostly alone, I get this. So if I plug in a negative x, what I would hope to see is that it'd be the same as if a negative had just been like pulled out to the front. But we're not seeing that happen. Because if I plug in a negative x, I can get this, but that's not the same as this, right? So it's not like a negative has pulled out to the front. So that's why they're not the same. It can be a little weird to test the origin when your y is like in the actual function part. My last type that I'll look at is we'll do x cubed plus 3. And so for the properties, I want to see if a negative y is the same as a positive y. Well, if I plug in that y as negative, I'm not getting the same, right? Because I should see it be the same as the regular f of x, and it's not. So doesn't satisfy. Let's try for the even function. So if I plug in a negative x, is it the same as if I did a positive x? Well, negative x cubed is the same as negative x and then cubed. So no, it does not satisfy this property. I don't get the original back. And lastly, let's go ahead and try checking out the origin. So again, I'm going to plug in a negative x. And so this one, I get y is equal to negative x cubed plus 3. But be careful, this is not the same as if I look at the original and had a negative pulled out all the way to the front. These are not the same. So this does not satisfy. So what we're going to see for this one is it doesn't have any symmetry, and that's fine. This one does not have any symmetry. Now, x cubed by itself, you would have had some symmetry because you just wouldn't have had this plus 3 on there. So imagine for this one, if we just didn't have this plus 3, then yes, we would have gotten negative x cubed is the same as having a negative outside of x cubed. So we would have seen some symmetry there. So I just wanted to show you one where maybe we don't have anything. And that's okay. It just doesn't have any symmetry. Let's do another example. And this one I'm only going to worry about if it's even or odd or neither. So determine if it's even, odd, or neither. And so I want to remind you, for an even function, the property that we're going to see, here, let me try to keep my colors the same, is this property here, that plugging in a negative x would be the same as plugging in a positive x. For odd, we should see that plugging in a negative x is the same as pulling a negative out to the front. And then neither, we're just going to see neither of these things happen. So A, let's do f of x is equal to negative 2x to the fourth plus 5 absolute value of x. And so the nice thing is when you're testing if it's even or odd, it's the same process. Like we're just going to plug in a negative x and see what happens. So plugging in negative x, so that's going to give me negative 2. Everywhere I see an x, I'm going to write negative x instead. And let's see how this simplifies. Negative x to the fourth is the same as x to the fourth. I don't really need those parentheses there anymore. And then absolute value of x, negative x, is the same as absolute value of x. So this one, we're seeing that it's the same as just f of x. So this is an even function. Let's do part B. This one says g of x equals 4x cubed minus x. And so again, I'm going to plug in a negative x. So I get 4 negative x cubed minus negative x. And if you want to call this g of x as well, that's fine. I wrote f just kind of out of habit, but technically it's g of x. So I'm just simplifying here. So negative x cubed, that's the same as saying negative x cubed like this, plus x. I can pull that negative out to the front now. So negative 4x cubed plus x. And so if we look at this compared to my original, you see how both the signs just changed? Well, that means this is the same as negative g of x. So this is an odd function because we saw all of our signs flip. And then I have one more to try. This one says y equals 2x squared plus x. So again, we're going to go ahead and try to plug in a negative x. I'm going to say just f of x for this. But I get 2 negative x squared minus x. If I simplify this, I get 2x squared minus x. You see how neither of this, like only one of the signs changed, not both of them? This means this is neither. Because if they had both been the same, it would have been an even function. And if they had both been different, like if there was a minus right here, that would have been odd. But since only one of them changed, this is neither. Alrighty, so that's about symmetry. The next type of stuff that we're going to look at is when to tell if a function is increasing, decreasing, or if it's constant. Suppose I is an interval contained within the domain of function f. This is very mathy language. What I want you to really know is that we're just looking at a piece of the graph. We're saying I is some interval. So we're just looking at a piece of our graph. That's it. I know it sounds all mathy and stuff. And then we're saying it's within the domain. Okay, so it's on the graph. If it's in the domain, then that means it's been graphed. F, so our function, is considered increasing on the interval I if f of x1 is less than f of x2 for all x1 less than x2 on the interval. Again, this sounds super mathy. All this is trying to say is, hey, if your x's are getting bigger, your y should also be getting bigger. And then you have an increasing function. So I know the language is a little, it's starting to get a little more mathy, but all we're saying is what's happening here is as x's increase, my y's also increase. So we would call that an increasing function on that interval. Now we say that f is decreasing on our interval I if f of x1 is greater than f of x2 for all x1 less than x2 on our interval. Again, all this is trying to say is as your x's are increasing, your y's are decreasing. That's all that's happening. Then we have if it's constant. We say that it is constant on an interval if your x's are equal to, if your y's, are equal to each other for all of your x values. So for this one, what we're seeing, basically we're going to see like a horizontal line. Really, this all kind of goes back to slope. Like if you think back to our lines and stuff, it's just that we often word it like this whenever we're dealing with more general functions. Like we call it slope and we call it positive slope and negative slope. whenever we're dealing with lines. But whenever we're dealing with more general functions, like not necessarily a line, we use this other language of like, oh, it's increasing or it's decreasing or it's constant. Now, some cool stuff can happen. So if our graph switches from decreasing to increasing at, say, a value x, then we would say that y value, f of x, is a relative minimum. And let me explain what's happening here. So basically what's happening is we're saying, okay, our graph is decreasing, so it's going down in some way. And then it gets to this certain x value, and then it starts going up. So at this x value, wherever it changed from decreasing to increasing, that is going to be considered our relative minimum for our y value. But be careful. Whenever you talk about minimum or maximum, those are always y values, not x values. Whenever we talk about minimum or maximums, it's because we say it's a y value because we're reading like up and down. Now, if your graph switches from increasing to decreasing, at some x value, then we would say that that y value that matches that is called a relative maximum. Again, remember f of x is just a y. And so what's going to happen here is like we're going up, 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 up. Oh, and then at some point we start going down, 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 down. It's that x value, wherever that change happened, that's our maximum point for our graph. But remember, it is the y value, not necessarily the x value. That is the actual max or min. Now we'll expand on this a little bit more later. We won't do too much with it right this second. I wanted to go check the homework again. I mean, when I wrote all these notes, I did check the homework, but it's been kind of a while now, and I've taught too many sections, and I can't remember like what the homework actually looked like. So I'm actually pulling it up right now. You might be able to hear me typing. I just want to see if there's any questions about this that I should probably cover, or if it was okay. So I know I'm just talking, but I just want to make sure. I usually would have added in like a example or something if they actually talked about anything, but I don't want to move on from it if there actually is some stuff. Okay, that's a symmetry question. Ooh, there is a question on here, and I didn't do it. I didn't make an example. Shame on me. Okay, let's go ahead and do one like this. I know y'all can't see what I'm doing, but I'm going to make something up. So I'm making up an example right now because I want to make sure you can do the homework. So example 3, I'm going to add this into my notes. I can't believe I didn't. It says determine on which intervals the function is increasing. We'll mess it with it a little bit. Decreasing and constant. Oh, this is kind of hard to type in. I wonder if I should show y'all. I don't think I can show you actually. It's a little weird to type in. So just be careful when you're typing this into the homework. But I'm going to draw us a little graph. Sorry for being kind of sporadic today. I didn't realize that I didn't make one of these, but I'm kind of glad I checked the homework real quick to make sure that I do something like this. All right, I'm going to put a point right here, and I'm going to highlight this point for us. I'm going to write what the point is just in case you can't tell. This is negative 3, 1. And then I'm going to put a point. Let's do one right here. We'll make this one 0, negative 2. And then let's do a point maybe, I'm just making stuff up, y'all. 2, 5. Then we'll come over to the point 4, 5. Then we'll come back down to 5, negative 1. Okay. And I'm going to draw this out. So here's what we're doing. I'm going to connect all these points. All right. Here's my graph. And so I want to know, where is the function decreasing? Where is it increasing? Where is it constant? And so for increasing, I want to look anywhere where it kind of looks like it has a positive slope. And you'll see these with curves and stuff as well later, but for this one, it just happens to be split into lines. So I'm only increasing right here is the only time I'm like going up. And so the interval in which that is happening, they're going to want the x values. So that happens from 0 to 2. So make sure you type this in right, and it is brackets. Then we'll do decreasing. So I'm going to use another color here. So for decreasing, I see that happen twice. It happens right here, and it happens here. So my first interval would be negative 3 to 0. And then they have you split it up with a comma if there's another one. So my other one would be 4 to 5. And so these are the x values, is the intervals that we're talking about. And then for constant, that just means where it's a straight line. And so that's happening only right here. And that is from 2 to 4. So there's a question similar-ish to this on the homework. So I want to make sure that y'all are able to do that one. And then there's also like a multiple choice one, but that one, if you could do this one, you'll be able to do that one. Something else I can highlight for you is that we do have some minimum and maximums going on. This right here is considered a relative maximum. I'm sorry, I didn't mean to say maximum. Relative minimum. Relative minimum. So what's that y value? So that's -2. So f of 0, which is -2, is a relative minimum. Now, the homework doesn't ask for that, but I do think it's interesting to know. And that's because we went from decreasing to increasing. So you can see that it's like a really low point of the graph. Now, we actually don't have a relative maximum because there's nowhere where we go straight from increasing to decreasing. So you might think like, oh, what about these up here? Wouldn't those be maximums? No, they don't go from increasing to decreasing. They go from increasing to constant. And that's not necessarily what we're looking for a maximum. Now, later in your lives, if you go on to Math 240 and Math 241, you'll go a lot deeper into minimums, maximums, and what's the difference between a relative maximum and minimum and a global minimum and maximum. We're not getting into all that. We're just looking at a little bit. Alrighty. So this is it for that little subsection. Last subsection is to talk about piecewise functions. Piecewise functions are functions that are broken up into pieces based on their interval. So I'll show you what I mean. So we'll do an example. So it says evaluate the function for the following. And so I'm going to give you the function first. The function is f of x equals, and I'm going to have like pieces of this. So it says it's negative x minus 1 for x less than -1. It's -3 for x between -1 and 2. You'll notice that it's included for the -1 here. And then it's square root x minus 2 for x is greater than or equal to 2. So this is a piecewise function. It just means the function's been broken up into pieces based on whatever you want your x to be. But we're going to do some evaluating. So for part A, we're going to evaluate f of -3. B, we'll do f of -1. C, we'll do f of 2. D, we'll do f of 6. So I just made a few of these. So for -3, that is going to fall into this category for the x's. So less than -1. So that means I'm going to use this function for this evaluation. So this will be negative, and I'm plugging in -3 for my x, minus 1. So I get +3 minus 1, so 2. For part B, I'm plugging in -1, And so now that I've done one part, you should pause and try to do the rest of them yourself. But -1 is going to fit into which category? It'd be this one. So I'm going to use this. Well, it's just -3 then, because there is no like x value to plug into. Two is going to fit into this one. So I'll plug it into square root 2 minus 2, which is square root 0, which is just 0. 6 also falls into that third one. So square root 6 minus 2, so square root of 4, which is 2. And that's it. So that's evaluating a piecewise function. I've done real life applications of this type before in Math 125. And something that we look at is like, it was like a tax problem or something. It was like, based on your income, you'll be split into these like taxes brackets basically, but it was like modeling. And so that would be kind of a real life example. Like, based on how much money you make, you're going to get taxed differently. So this would be an example of like a piecewise function in real life. Next, let's look at graphing piecewise functions. So I'll just say graph, and we'll do a few of these. So part A, f of x is equal to -3x for x less than 1, and it's -3. My marker keeps going out. For x greater than or equal to 1. So I'm going to do my sketch. All right. Something to think about whenever you do a piecewise function is this area right here is going to be very important. So where the function is breaking off into different like looks, I guess you could say, is going to be important to us. So usually what I like to do is I like to use that value and plug it in for each of my pieces. So I'm going to do this one in pink. And so I'm going to plug in 1 for my -3x. If I plug in 1, I get -3 times 1, so that's -3. So this is the point 1, -3. Be careful though, the 1 is not included, so that's going to have to be an open circle right there. Then I'll graph the rest of it. So this is a line, so I'll use slope. So this is a line, so I'll use the slope. And so the slope for this line is -3/1. And then you want to think, okay, should I be going to the left of this one or to the right of this one? Because it's less than, I'm going to move to the left of this one. So I'm going to use my slope to make a new point. So I'm going to go up 3/1. So my next point would be right here. Did I mark that right? Hold on. I feel like I went up a little too much. Yeah, because look, I went up 4 on accident. Oh, goodness gracious. Should be right here. Should be right here. Thank goodness I have my notes in front of me to fix my silly mistakes. I don't know why I did that. I just was looking at it wrong. And then I can go up again. So if I want another point, 1, 2, 3 over 1. So that one would be like here. So here's what my pink part of my graph is looking like. Now I'll do the rest of it. Let's do this one. I'll do in green. And so still, I would plug in the other point, like 1 again, but for this one, I just get -3 because there is no x. So that's going to be a closed circle here. And again, this is a line. Remember, this is a y equals line because this is the same as saying y. So this is a line. Y equals -3 is just a straight line, horizontal line. So this is using a good bit of like kind of stuff that we've previously done. So if you didn't feel good about the line stuff, you would definitely struggle with this part. And I feel like it is a little weird, you know, like we're not using, even though we're dealing with lines, we're not like using the y-intercept. And it's just because you kind of have another important point to worry about, which is where the graph is breaking. Now, realistically, whenever you actually graph this, you would not have to have it in separate colors, you know, like this would be the same. It would be just a continuous line um, that just looks, you know, it would look like this. Oh, I didn't mean to have the eraser on. It would just look like this, basically. But I just do mine in colors. You see, every time I press that back button, it goes all the way to the top, and I don't know why. It happened with the last video too. What's going on? I don't like this. Frustrating me. Like it backs what I did, but it goes all the way to the top. Like why would I want that? All right, let's do another one. Let's do another one. So this one, I'll say f of x again. And this one is x plus 3 for x less than -1. And then x squared for x between -1 and 2. I'm just drawing my little sketch. And so this one we're also going to have to be careful because of this part right here. It means that the graph is not going to be able to go past +2. Like we're not going to have anything over there. So anytime you have like these end points basically on your intervals, we're going to want to watch that. All right, so I'll do this one in pink. And we're starting, we have -1 as an important point. So I'm going to go ahead and plug in -1 for that line. So if I plug in -1, I get -1 plus 3, which will be 2. So this is going to be the point, -1, 2. But be careful, open circle or closed circle. It's going to be an open circle because it doesn't have the equal to bar right here. So open circle. And then since it's a line, I can use slope, or you could plot more points if you want. You can do that for lines. So since this is a line, and I know that because the x is just x, it doesn't have like a power or a square root or like absolute value. It doesn't have anything like that. That's how I know it's a line. So my slope for this one is just 1 over 1. But be careful, I don't want to move to the right of -1. So like I don't want to go up. Like I don't want to do this. because that's not going to be correct. If I press back and it brings me to the top, y'all, I'm like scared. I'm like too scared to even click it. So since I only want to go to the left of -1, I'm just going to go like down and over, which is something I showed y'all how to do when we did the lines, that sometimes you may not want to go up, sometimes you want to go down. But here's what my line looks like over there. Then I'll do this one in green. And so this one has two important points, so I'm going to plot both of those. So if I plot in -1, I'm going to get -1 squared, which is 1. So that's the point -1, 1, which is right here. It is a equal to, so it's a closed circle. I'm also going to plot the other important point that it talks about, which is 2. So if I plug in 2, I get 2 squared, which is 4. So 2, 4. And then because it's a parabola, we also want to think about, because it's a quadratic, so it's a parabola, we also want to think about how we used to graph parabolas as well. So I usually would pick an x value that makes the inside part 0. So in this case, that would be 0. So 0 squared would be 0. So I get the point 0, 0 here. If you want another point, then plug in another point. So if we want to maybe, like, do we want to maybe do 1? Well, there I would get 1 squared, so that's 1. And so here's what my other part is looking like. But be careful, I actually don't want to go over that 2. And I also need to make a correction here. That 2 should be an open circle. I'm someone who, I can kind of make mistakes on closed circle, open circle. So I always just kind of check it at the end just to be sure. So because it said x is only less than 2, that's why I want to open circle right there, because it doesn't have the equal to, so it can't be closed. So just by habit, when I do points, I fill them in, but we actually want to be careful about doing that with a piecewise. We got to watch out for those equal to bars and stuff. So that's it for the piecewise functions and everything. So that's it for this section. Something kind of interesting that I want to share with you is, um, so this quarter was our first quarter using Alex, and it's also our first quarter using this textbook. We actually didn't do piecewise functions and symmetry and stuff to this extent previously to this. So I'm hoping that it went well for you. But if you have any questions, I mean, I always tell you don't hesitate to ask, but for sure for this one, because I mean, these are new notes that I wrote this quarter, and I haven't really gone into depth about this stuff before. So for sure, if you have questions, let me know, because in the past when I've taught a certain section, I already know what students struggle with on it because I've taught it before. But for this one, since I really haven't, I don't necessarily know what might be a struggle for you. So, just for the sake of having a better experience for all students, definitely let me know if y'all have any questions about these topics that I did today, because we haven't gone into depth about them in previous quarters. I did for like increasing, decreasing, but that's about it. So, okay, well, that's it. So, I hope y'all have a wonderful day, and I will see y'all in the next video, of course. Bye bye.